Good morning in Madrid, okay, and welcome to this first session of the AST Conference 2021 edition. Okay, this is the session on text generation, okay, and for this session we have two full papers and a short paper, okay, and we will start, okay, with the presentation on the paper titled Automatic Property-Based Testing of GraphQL APIs, presented by Stefan Carlson from Mallarden University. Okay, so Stefan, please, you have the stage when you want.
Thank you. So welcome to this presentation. This paper was written by me, Stefan Karlsson, and my colleagues Adnan Shoycevic and Daniel Sundmark. It was a collaboration between ABB and Mallarden University and the Knowledge Foundation. So first I will give you some context and some background, and then go into the proposed method, and then talk about the evaluation and results, and then a summary. So at ABB, we, among other things, develop process automation systems that control factory plants. So a new development in this area is that we want to upload data from the process control system via an edge to a cloud environment. This is done to enable mobile applications and web applications, among other things, to show dashboards and similar things. And a common way to upload data to the cloud is by REST APIs, a common type of web APIs. And for the consumption for the clients, it's also very common to use REST APIs. And increasingly, GraphQL, that will be the theme of this talk, is used more and more. But before going into GraphQL, it's relevant to talk about REST, since GraphQL is usually addressing some shortcomings of REST. So REST is a typical interface nowadays, both for internal platforms in a microservice architecture and also to talk to cloud-based services. It stands for representational state transfer, and it's an architectural style, so it's not a protocol, but it leverages the HTTP protocol to manipulate resources. So you might be familiar with this already, but you can, for example, get a list of products via an URL. You can get specific items with an ID in the path. You can also create new resources by posting and giving input data. And you can also delete resources. So REST APIs are very common for internet-based services and used by companies such as Google, Facebook, Twitter. And it has a large ecosystem of tools and frameworks and libraries. So there's lots of leverage to use this type of API when building systems. But REST has some drawbacks. And a common such drawback is the problem of over and under fetching. This means that the client will either get too little data of what was needed for the client or too much. And it's reported in the literature some examples of where the client receives up to 90% more data than was needed. So there's a lot of waste in network resources there. In addition, a client has no control of the shape of the data. The server implementation dictates what the shape will be of the response to the client. And also, if a client requires more or less information, the server API needs to change to reflect this. It's also very common that the client need to do several round trips to get a complete picture to solve the client problem. So for example, if you want the pet of your friend, you first might need to get the actual person, then you can get the friend entity of that person, and then you can get the pet of the friend. And it might be a lot of intermediate state here that you need to keep in the client, increasing the complexity of the client solution. And there's no schema in REST. So there are ways to address this with OpenAPI and Swagger, but it's not mandatory. So there's no way other than documentation for a client to know what operations are available. So GraphQL then was publicly released in 2015 by Facebook to address a lot of these shortcomings. So it's currently hosted by GraphQL Foundation, and it's a schema-based query language. So here in GraphQL, we have a typed schema. And due to this schema, a client knows what it can do and what type of data it can get. So now the client can fetch only the data it needs by selecting only the fields from specific objects that are relevant. And in this way, the client do not need to keep track of these intermediate states. It can pull directly into the graph of the data and get down to the details it needs to solve the specific use case. The client now also knows the shape of the response, since the shape will reflect what the client did query for. So much of this complexity of intermediate state and query resolution is now moved to the server. So on the right, there's an example of types in a schema. The root always starts with a query. So from the query root, you can here select a hero, that's a character. And the character has fields you can select, like name and friends. And friends is another complex type. So you can select again a name of the friend. So to the left in that picture, you can see an example of a query that will get you all different kinds of data in this domain. We have also used property-based testing. And in the literature, there are multiple reported case studies of finding faults in industry-grade systems. And that's interesting and important for our context at targeting industry-grade systems. And the first property-based testing tool is QuickCheck. And now it's a very available technique. There are about 40 different language implementations of QuickCheck-like libraries. And while using these kind of libraries, they provide basic generators that you then can combine into your domain-specific generators. You then use these generated values from the generators, and you check properties of the system under test. So such a basic property would be that the system should not crash given generated input, for example. But they can also be more complex properties. So what these libraries also do is that if a property fails, it will try to shrink the failing case into a minimal reproducible example. So that is usually very useful from a developer perspective when you can go down from a large case to a much simpler case for debugging or error reporting. So our proposed method is then to automatically create property-based generators from a GraphQL schema. We then use properties to check for internal server errors, and that is when with a HTTP response code of 500. So it typically indicates a crash. We also have properties to check that the returned data from the API actually conforms to the schema. We also allow for some custom generators. So, for example, a situation where you would like to need and use a custom generator is that in the schema, a type of a field could be a string, but you as a human user of the system, you know that this has to be a special kind of string. We should not just randomly generate strings maybe the string need to start with ID : / and then a number. So in that way, you can make this more efficient and hand us a custom generator. So the main challenges we addressed was to generate queries that must conform to the schema. Otherwise, if it's not a valid GraphQL schema, it will typically be stopped at the door in a validation step in GraphQL frameworks. So we will not reach the system under test if it's not valid. Also, it's typical in industry-grade systems to implement complexity limitations. So this means that in order to protect the service from denial of service attacks, you will limit the complexity of a query. So in practice, this means that if the query is too large or too deep, it will just be rejected and you will not get a result. So we need to take that in consideration when generating queries. Also, there's a graph-like nature to the schema. It can also be recursive. So we will need to have to take that into consideration when generating queries. We have to stop somewhere. And also, depending on where we stop, we might need to reform the query into a valid query. Because if you stop at a complex object, you must select a field or remove that object, since otherwise it's not a valid GraphQL query. You always have to select a field from a complex type. So an overview of the method is that as input, we take the GraphQL schema. We create validation specifications of each type in the schema. These are later used for the verification of the responses. Next, we create automatically these query generators from the schema. These are then used to generate query nodes. And here we can optionally take these custom generators. The next step is to format these nodes, the generated nodes, into an actual query. And we then run this query on the system under test and verify our properties on the responses. So to the left is the generated nodes. So lots of stuff there. But there's a graphical representation to the right, where the generated nodes, we have a project as the root object, where we can select another complex object as members here. And there's also fields with description and name. And here a project was also generated, but we have to remove that since the inclusion of an object without selected field would result in an invalid query. So the end result is at the bottom right, where we have an actual GraphQL query that we can send to the system under test. So in addition to generating the node and the structure of the query, we also generate input values. So in this case, the value of this ID is a string, so that's also a generated value. So in order to be able to assess the method, we also proposed a schema coverage measurement for black box testing of GraphQL. And since it's a recursive schema, the potential search space is infinite. So what we did was to create a tuple pairs of each unique pair of object and fields in the schema. So in this example, we have a hero can have a name and hero can have friends and so on. We then collect these same kind of tuples from the generated queries, and the coverage is then calculated based on how many of these tuples are covered. So to make sure that you cover all types in the schema. So for our evaluation, we had 2 research questions. The first one was what schema coverage can we achieve with this method? We evaluated that on GitLab. And GitLab is an open DevOps platform. It's industry grade and well used, and it also has an open source implementation, so it was convenient to experiment on. And the second research question was what fault-finding capability we had achieved with the method. We also evaluated on GitLab and a more controlled example. So for the schema coverage result on GitLab, here in the table, the size determines the size of generated values. So that is both the size of the query and the size of the values. As a larger size of a string will give you a longer string than a shorter size. The max limit determines the allowed query depth. So there's then this trade-off between the size of the query and the complexity guards of your system under test. So these need to be tweaked for your specific system under test. But we found for our system under test here, GitLab, we had a nice trade-off with a recursion limit of depth 3, that you can go 3 instances down in the query, and about size 100, 1000. Then we could get the schema coverage fully done within a few seconds. So for the fault finding, on the controlled example, we had 15 bugs injected. There were input validation bugs, logic bugs causing a crash, and logic bugs in the domain where the wrong result were returned, maybe a 4 instead of a 5. And the 4 bugs are returning the wrong type. So we could find all bugs except the domain-specific ones. We didn't know the correct answer to a query there. So there we need a stronger domain-aware oracles. And it's a common Oracle problem in test automation. So for the fault finding in GitLab, we found 8 new bugs that we reported back to GitLab. And several of them raised discussion among the developers, and they implemented fixes for them. And they even discussed how they could improve their testing to catch these kind of errors. So some examples here that we found is a crash here where we pass in a null byte. So this is a generated query to the system under test. And we got some recognition from the developers that they should handle this in a more graceful way with better input validation. Another example is here that the ID in the generated query has the wrong type, also resulting in a crash. And here we can see that they implement better error handling. And also at the top on the right, test activities planned. They are planning to increase the test suite to handle this kind of testing. And the last example is also input validation, where a fix has been merged into the production system. So to summarize, the contributions we made is an automatic approach to generate test cases from a GraphQL schema. We also proposed a method of measuring coverage for black box GraphQL test generation. We evaluated on an industry-grade system where we found faults and reported the faults, and they were fixed by the developers. And also, it's a nice contribution, I think, that we made developers aware of gaps in their testing. So some ideas of future work is to improve support for domain-aware properties, that maybe the user can handle those kind of properties. And for the coverage criteria, we could potentially include coverage of subgraphs that might be of special interest to the user. And for the complexity guards, we could potentially automatically try to adopt the test generation process if we hit the complexity guard, then back down, and so on. So with that, I thank you for your attention. And if you have any questions, I'm happy to answer them. And if you have any questions in the future, you're happy to contact any of us. So thank you.
Thank you, Stefan. So, time for questions. We have about 8 minutes for question and answer. So while people write down their questions, let me start. So, do you take into account when building generators? Okay, if the data that is returned by the API, okay, is correct, because I see there are some issues with detecting domain bugs. Okay, and I don't know exactly which specific data can you check with your method, or this is completely ignored.
Yeah, so we check that the returned data conforms to the schema. So if we make a query and we get back a person, then we will check that the person's name, for example, actually is a string and the age is an integer according to the schema. So we cannot check if it is the correct name, but we can see that it is a name according to what's given in the schema.
Okay, understand. On the all bugs that you reported to GitLab, were all them fixed, or do you have an idea?
Yeah, I think some of them they were lumped together. So if we look at the 8 reports, not all of them have a fix, but I think most of them are fixed when other ones were fixed, so to say. So they made an epic out of addressing these input validations problems that we showed.
Okay, we have a question in the chat. Okay, Mike asks, is the code to generate tests from GraphQL schema open source?
Yeah, there's like a research prototype. It's you can find a link in the paper, but it's it's a prototype. So you still need some developer skills, I guess, to use it effectively. So, but it serves as an inspiration, and you can see the work there. But it's not a off-the-shelf tool. So hopefully we can make that better in the future as well. But at least it's an inspiration for anyone interested.
Yes, and Breno, congratulations you for the presentation, okay, and all the authors. And he asked if you could please elaborate a bit on the future work you mentioned on covering subgraphs.
Yeah, so now we just, as I described, we check that all types are covered. But there might be that if you have a special graph that you're interested in, for example, that I want to make sure that the person, we get the friend and we get the pet's name. That's important in my domain, that we make sure that you cover that graph. Because now we can say that we cover all types, but that doesn't mean we cover every permutation of graphs that would satisfy those type coverage. So that might be an improvement then.
So basically, you mean covering all possible permutations of how you can traverse, right? The schema, right?
Yeah, since it's a recursive schema, and so we cannot exhaustively do it depending on the schema. But then you could maybe mark a path as this is an important type of query. So please make sure this is covered in your test generation.
And Xavier, thank you as well for the presentation. Okay, and he says your work reminds him of grammar-based fuzzing or generating formatted inputs. Have you considered using such approaches?
Yeah, it's kind of the line between fuzzing and property-based testing is not always clear. But I think where property-based testing we start out now pretty close to fuzzing, but property-based testing allows usually for the user providing custom generators that might be more suitable to the domain and might be able to provide more properties, going not just doing fuzzing, but more domain-aware testing as well.
You can just another question, because when you talked about coverage, your metric, okay, about coverage of the schema, okay, I was thinking about the similar reports that we can get from usual testing tools, like for instance, I'm used to Java, so JUnit, for instance, or the like. So have you considered, for instance, doing such an integration, so these people, for instance, at GitLab could have a coverage report out of the box? I mean, okay, without they probably having to doing some adaptations to include your tool, okay, into their continuous integration approaches.
Yeah, so it would be interesting to also have more white box coverage. Now we did it like black box, so we didn't have any access. We since it's open source, we had access to the source code, but we pretended we were keeping black box because for ABB, for example, they don't have the same implementation language as GitLab. But for sure, it would be interesting to also get that kind of coverage. Since we now do the test generation and we run it on the running service, then if you have like Java or Ruby, you can do auto process code coverage. I don't think you can do it the same way in C#, but if you can do that, it could be applied quite easily, I think.
I think that could foster adoption of this kind of approaches. Okay, so there are no more questions. Okay, the schedule is a bit tight, so I have to move to the backstage for the next paper. But remember that once this session ends, okay, the author will be transferred automatically to a discussion room, and all the attendants, okay, can join that room if you wish to ask some other questions. Okay, so I will leave the message here. Okay, and I will leave you now, okay, to go to the backstage and prepare for the next paper in this session. Okay, thank you very much, Stefan, for your presentation.
Thank you.
path